parallel lines and perpendicular lines, and the amazing math about their slopes. California Algebra I Standard 8, starring yours truly, Dr. James M. Nuclear here, for Whalebone IR and software, and math itself. Today, we're going to talk about parallel lines and perpendicular line. Here's a Cartesian plane right here. Here are one line, and now I'm going to put up a line that's parallel to it. Notice they run right alongside of each other, and the distance between them never changes. Now, they don't have to be pointing in this direction. I could take those lines and I could put them like this, or I could put them like this, or I could raise them up or lower them down. I could even spread the lines further apart from each other if I wanted to, and they might still be parallel lines. The only thing that makes lines parallel to each other is that they're on the same plane, they're on one flat surface, and the distance between the two of them never gets any different. It always is the same. That is to say, they never get further apart from each other, they never get any closer together, and they lie on to get. Here it is as it's stated in the content standard document. It says, students understand the concept of parallel lines and perpendicular lines and how those slopes are related. Students are able to find the equation, we'll get into that in a moment, find an equation of a line perpendicular to a line that passes through a given point. Let me highlight those. Okay? Now they get the heavy math. Woo! Heavy stuff here. Give me an equation of a line that is perpendicular to a line with this equation. Okay? As we know, lines on the Cartesian plane have an equation that relates to them, that will generate points that form that line. Here's a line that has a slope of 1/2, because that's where the slope goes, multiplied by the x, and it has a y-intercept of 4. That's not too important. We need another line that is perpendicular to this line, but passes through this point. Let's take a look at what this looks like on the Cartesian plane. Okay? Here is our point that's given to us, 2, 5. It's at x equals 2 and y equals 5, and there it is, a little dot. Here's our equation line. It goes through that point, but we're looking to draw a line that will form a 90 degrees right here and be perpendicular to this line, but also have the very tough requirement of going exactly through that point. And we'll have to use a particular form of a linear equation to get this done. Now the slope of the original line is 1/2. The slope of our new line has got to be a negative reciprocal of that line if we expect it to be perpendicular. So we take the 1/2, we flip it around to get the reciprocal, we slap a negative sign on it to give us the negative, and what do we get? Negative 1/2 this should be. No, I'm sorry. Negative 2 is proper. We started with 1/2, we flipped that over, that got us 2, and then we took a negative of that gives us negative 2 as the new slope. Let's plot a few points. If we start at that point given, which was 2, 5, the slope tells us to go down 2 over 1. We get a point right there. We go down 2 over 1 again. We get a point right there. Down 2 over 1, another point. So we can now draw a perpendicular line through those points. And look how nice and 90 degrees it is with our original line. See, the math works from a drawing perspective. We got to go farther than that if we're going to get up to the standard. So here we go. We need to find out not only what the picture looks like, but we need to find the equation of this new line right here. We know some things about it already. We know that this point is in it, And we know that its slope is going to be -2. We need an equation though. There is a form of an equation called a point-slope form. And one of its main purposes is to take care of this problem for us. The slope and a point is what we need to know. We plug them into the new form, and we'll be done. We're almost done. Our slope is -2. Our point is 2, 5. Now here's the form itself. Don't get scared. I know it looks pretty nasty. It is pretty nasty, but it's not too hard to deal with. We have here y minus y1 equals m times, in parentheses, x minus x1. Now, the practical upshot of this is we could read it as y1 means the y of our point, or the y of point 1. The x1 over here, on the other hand, we read that as the x of our point, the x of point 1. And the m, as it is in many other places, is the slope. So, what I'd like you to think about these equations is this. There are certain things in this form that are going to change, and there are certain things that stay the same. So, if we can get a good shot of this, then you can see that this is the same form we've been looking at. Here it is completely written out. Then what I've done here is showed you that the things that change, there is a box here, and a box here, and a box here. Those need to get filled in with new information. Now the y and the x and the minus sign and the minus sign and the equal sign and the parentheses, all that sticks around. Those are the formula. That's the template that we use. But what goes in the box here and there, that changes depending on what line we're working with and what point on that line we want to talk about. So let's put this in action. We have the format. We have x1 and y1 are going to be replaced. This x1 here going to go away. y1 here going to go away. The m is going to get replaced. That's going to go away. Think of a hole being there. But don't think of a hole on this one or this one. Though x and y are not touched by this process. They're going to stay in our final equation. They're still going to be there. So, putting in what we have, our point was a 2, 5. 2 is in the x location, so 2 goes in where x1 goes. 5 is in the y location, so 5 goes in where y1 goes. And we figured our slope, since it's a negative reciprocal of the original line, we got a -2 for our slope. Slope goes in where the m goes, -2. Now all we have to do is move the 5 over to the other side, do the math distributive property, and we can move this into a y equals mx plus b format. So we have y equals -2x plus 9. How do we get that? Well, -2 times x is -2x. -2 times a -2 is a +4. And then I add 5 to both sides. The 4 turns into a 9. The -5 goes away on this side. Finally, I get y equals -2x plus 9. So this is a perpendicular line to our original line. It goes through the point that we needed to go through. And furthermore, we moved it into y equals mx plus b format to make it easy to draw. That's it. That covers the whole Algebra 1 number 8 standard. If you missed any of it, go back. Rewind. Rewind. Go back this way. And you can see it over and over again. Let's review right here. Parallel lines never touch each other. They never get closer together. They never get further apart. They run right alongside each other forever. Perpendicular lines meet at one point and form a 90-degree angle, also called a right angle. Perpendicular lines have slopes that are negative reciprocals of each other. That is, you turn that slope into a fraction, if it's not already a fraction. You flip that fraction over, that gives you reciprocal. Then you slap a negative sign on it if it didn't have one, or you take a negative sign away if it does have one. That gives you the negative. So then you have a negative reciprocal slope, which gives you a perpendicular. What else did we learn? Well, there's a point-slope form for linear equations, and we can use this point-slope form to satisfy the standard. That is, we can use it to find a line that goes to a certain point and is perpendicular to that line at that point. It reads like this: y minus y1 equals